Hi friends, welcome to another lecture. Today is the first video in series of control system lectures for GATE, IES and other such competitive exams. In control system, the major focus lies on finding location of poles and analyzing their effect on stability. So to begin our lecture series on control system, we will first understand what exactly are poles. So let's take a transfer function and plot it. When we plot the transfer function, we see that there are 5 vertical columns rising from the surface. So in short, poles are such input points for which we get unusually high output. But if for all poles we get high response, then why are we so concerned about location of these poles? To understand it, consider a ball falling freely from sky. You will notice that the amplitude of ball bounce reduces for each bounce. Similarly, you can see a pendulum system. Even its oscillation angle decreases with time. Now if we plot a curve through peaks of these response, we can see there is an exponential function with -a term in the exponent. On taking Laplace transform for this, we find that it's a pole in the S pole on the left hand side of the imaginary axis. Therefore, we can see that for the poles on left hand side of the imaginary axis, even if the response is unusually high for poles, this high amplitude will decrease with time. Therefore, such poles can be considered as a stable poles, and such systems can be considered inherently stable. These systems have the capability to withstand a sudden force and come back to their stable positions. But if we take a pole on the right hand side of the imaginary axis, you will see the inverse Laplace transform will have an exponential function with a positive exponent. Therefore, the output response of these poles will continuously increase with time, making the system unstable. Therefore, we need to get rid of such poles, and that is why it is essential to find the location of such poles and see how we can remove them from the systems. Now to understand how does the pole affect a transfer function response, let's take an exemplary transfer function 1 upon s square plus 1. When we plot the response of this transfer function, we can see that it is a sinusoidal response with amplitude from 1 to -1. Now we will add a right hand side pole s minus 6 to this transfer function and we will plot the response. On plotting the response, we can see that the response reaches a very high magnitude in a very short period of time. Thus, adding a right hand side pole to a transfer function makes the system unstable. Now we will add a left hand side pole to this transfer function, that is s plus 6. When we plot the response for this transfer function, we can see that the response of the transfer function is still a sinusoidal function, but the amplitude has reduced from 1 to 0.2. And there is also a minor decrease in the frequency of oscillation, which is not noticeable from the plot. So thus we can see that adding a left hand side pole to a transfer function reduces instability and thus increases the stability. Therefore, it makes the system more stable. Now let's take a practical example to understand the significance of poles. It is a well-known fact that soldiers are not allowed to march on bridges. Let's try to understand why. Consider a bridge system as shown in the figure. Now, if a vertical force is applied at a point A, the bridge will oscillate as shown in the figure. Now if we plot the oscillation of point A with time, we will find it is a sinusoidal function of time. In this plot, the velocity is 0 at the peaks and velocity is maximum at 0 displacement positions. Therefore, when the point A moves from the peak position to 0 displacement position, its velocity increases. Therefore, this is an accelerating zone. On the other hand, when particle A moves from 0 displacement position to negative peak, the velocity of point A again decreases to 0. Therefore, this is a deaccelerating zone. Now, Let's consider the force applied by the soldiers while marching. As you can see from the video, this force is rhythmic and we can assume it to be a sinusoidal force. Now consider the equation of bridge and soldier system as shown here. Where Wf is the frequency of force applied by soldiers and omega f is the natural frequency of oscillation of the bridge. Now when omega f equal to omega, that is the frequency of force applied by soldiers, is equal to the natural frequency of oscillation of the bridge, we get a large response. As you can see from the simulation, where the yellow line is the force applied by soldiers march and the blue line indicates vibration amplitude of the bridge. Even though the amplitude of the force applied by soldiers march is small and of fixed frequency, the output of vibration continuously rises. It becomes large enough to break the bridge, and that is exactly why soldiers are not allowed to march on a bridge. To practically understand this phenomena, let's go back to our previous diagram and use this response curve in understanding the cause of increase in vibration amplitude. In the figure you can see a lag between yellow line and blue line. This is because yellow line is the input while blue line is the output, therefore the system has some lag. Now taking the blue curve, we can see that these are the deaccelerating zones in each cycle. Now suppose that the soldier's march frequency matches with the natural frequency of the bridge and the forces applied by them is shown by yellow arrows. Now due to this force, in each cycle the velocity of particle A will be higher than the velocity without force in the deaccelerating zone. Thus in each cycle point A will reach a higher negative peak than it would have achieved without this force. As this phenomena repeats over each cycle, the amplitude of vibration increases in this cycle. It is because of this the amplitude of vibration continuously increases to an amplitude which can break the bridge. Now let's take a second case where the soldier march frequency does not match with the frequency of oscillation of bridge. Then you can see the small yellow arrow showing the force applied by the soldiers. Here you can see that even though the negative peak is higher than the normal peak without the force, but the positive peak will be reduced due to presence of a second force. Similar process will repeat over each cycle and therefore the amplitude will not increase continuously. From this example we can see importance of poles in designing of systems. Thanks for watching the video. In following videos we will discuss about root locus, Nyquist state variables and other topics related to control system. Please like and subscribe this video. Thank you.